Welcome to this deep dive into quantum machine learning. It's this really fascinating intersection, isn't it, where quantum mechanics meets machine learning.
It really is. And your sources definitely paint a picture of something potentially, well, game-changing, not just a small step up.
Right, like it could help us tackle problems that are just completely out of reach for today's computers.
Exactly. Think about classical computers. They work step by step, bit by bit. But quantum computing, it uses these fundamentally different phenomena.
Which gives us that quantum advantage idea we hear about.
Precisely. The potential to solve things that are, frankly, impossible for even our best supercomputers today.
Okay, let's break down the quantum side first then. Our sources really stress the role of qubits. How are they different from regular bits?
Well, a classical bit is simple, right? It's either a 0 or a 1, on or off. But a qubit, thanks to superposition, it can be both 0 and 1 at the same time, sort of like a dimmer switch instead of a hard on-off switch.
Okay, both at once. How does that help?
It means a quantum computer, even with just a handful of qubits, can explore a massive number of possibilities all at the same time, in parallel.
So instead of checking one path, then another,
Yeah.
it's like checking many paths simultaneously. That sounds way faster.
It has that potential, yeah. And then you add entanglement to the mix.
Right, the spooky action at a distance thing.
Kind of, yeah. When qubits are entangled, they're linked. Measure one and you instantly know the state of the other, no matter the distance. It sounds weird, but it allows you to explore these incredibly complex relationships, these correlations within data.
Correlations that might be too hidden or complex for classical methods to find easily?
That's the idea. So QML wants to harness both superposition for that parallel exploration and entanglement for understanding those deep connections to really push machine learning forward.
Especially for huge, messy data sets, I imagine.
Exactly, where classical methods start to hit a wall because the complexity just explodes.
So how does this match with the machine learning we already kind of know? Like supervised, unsupervised, reinforcement, learning our sources, mention those.
Yeah, and that's important. The basic goals are the same, Learning from labels, finding patterns without labels, learning through rewards.
Okay.
What changes is the engine doing the work. We're looking at how quantum algorithms can maybe do the heavy lifting, the math, the optimization inside those frameworks, but potentially much, much faster or more efficiently.
And we see this popping up with tools we recognize, like neural networks, SVMs, PCA.
Right. And the fascinating bit is trying to translate those quantum advantages, superposition, entanglement, into real benefits for these classic techniques.
So like for quantum neural networks, they process things differently.
Exactly. The quantum circuit itself might represent complex patterns using fewer adjustable parts, fewer parameters than a big classical network would need.
Right. And for quantum SVMs.
They use quantum effects to handle something called the kernel calculation. It's basically a way to map data to make it easier to classify. And quantum computers might do that mapping much faster, especially if you have tons of features like, say, pixels in an image.
So it's less about throwing out the old rule book and more about maybe supercharging parts of it with quantum?
That's a great way to put it, yeah. Especially in the near term. Enhance existing methods by letting a quantum processor tackle the really hard computational bits. Not just for speed, maybe for better accuracy too, or finding insights we just can't see now.
Okay, this is where it gets really interesting. Let's dive into some specific algorithms our sources mention. First up, those quantum neural networks, QNNs.
Right. So think of classical neural nets with layers of neurons. QNNs use quantum circuits, sequences of quantum operations and qubits as their layers.
But instead of zeros and ones, they're manipulating superposition and entanglement.
Exactly. And the theory is, for some really complex types of data, a QNN might capture the pattern more elegantly, with less complexity in the network itself.
Which sounds great for efficiency. But didn't the sources mention a catch? Something about training them.
Ah, yes. The Barren Plateau problem. It's a real headache. Basically, when you're trying to train the QNN, adjusting its parameters, the landscape you're navigating can become incredibly flat. The signals telling you which way to adjust, the gradients, they just vanish.
So the learning gets stuck.
It can, yeah. It's like trying to roll a ball downhill on an almost perfectly flat surface. Very hard to find the right direction. That's why hybrid approaches are popular. Use a classical computer to optimize the quantum part.
Okay, makes sense. What about quantum support vector machines, QSVMs? You mentioned they help with classification.
They do. The key idea there is the quantum kernel. Classical SVMs use kernels to sort of project data into a space where it's easier to separate classes with a line or a plane.
Uh-huh.
Quantum kernels aim to use quantum computation to do that projection, potentially much more powerfully or efficiently, especially for data with really complex structures, like finding a clever way to untangle a knot by looking at it differently.
So the quantum computer figures out the best way to draw those separating lines in that complex space.
It does the hard part of calculating that transformation, yeah. The classification might still happen classically, but calculating that kernel quantumly could be much faster for training, and maybe even find better boundaries for tricky data sets.
Got it. And then there's quantum PCA, principal component analysis. That's about simplifying data, right? Reducing dimensions.
Exactly. Imagine a giant spreadsheet with hundreds of columns. PCA tries to find the few key combinations of columns that capture most of the important information, simplifying it without losing too much.
Okay.
QPCA looks at using quantum algorithms to find those principal components potentially much, much faster than classical methods. Think about processing huge streams of sensor data or complex scientific simulation results.
But I recall a note in the sources saying there's some debate about how much faster it really is in practice.
That's right. Yeah, there are caveats. The theoretical speedup is there, but actually getting the classical data into the quantum computer efficiently, that encoding step can sometimes eat up the advantage. It's still an active research area, finding the best ways to load the data.
So QNNs, QSVMs, QPCA, are there other quantum tools being worked on for ML?
Yeah, definitely. People are looking at quantum reinforcement learning, using quantum to help agents explore and learn optimal actions faster. Quantum Boltzmann machines for generating new data samples. Quantum K-means for finding clusters or groups in data.
So lots of different angles being explored.
Absolutely. Each one trying to leverage specific quantum properties for a particular kind of machine learning task.
This is the really exciting part for me. Where could this stuff actually be used? Our sources mention quite a few areas. Finance, for instance.
Finance is a huge one, yeah. You've got massive amounts of complex data, and the need for speed and accuracy is critical. So imagine QML building much better risk models, or spotting really subtle fraud patterns, or optimizing investment portfolios, considering way more factors than we currently can. Maybe even getting a tiny edge in predicting market swings. Even small improvements there mean big money.
It's like giving analysts superpowers.
Oh, yeah.
Okay, what about healthcare? Drug discovery comes up a lot.
That's an area with just enormous potential for impact. Simulating how molecules interact is incredibly hard for classical computers. It limits how we search for new drugs.
Right.
Quantum computers, theoretically, could simulate molecules much more accurately and faster. That could drastically speed up finding new medicines. And beyond drugs, think about analyzing complex patient data genetic, clinical to personalized treatments, or spot disease patterns earlier, maybe even improve medical image analysis.
Wow, that could change everything. What other industries?
Material science is another big one. Designing new materials lighter, stronger, better conductors relies on understanding atomic interactions. QML could allow simulations that lead to materials we can't even imagine yet. And things like logistics, optimizing delivery routes, managing traffic, supply chains. These are incredibly complex optimization problems where quantum could potentially find much better solutions. And just broadly, enhancing AI itself, better pattern recognition, more sophisticated language understanding.
The potential seems almost limitless. But okay, let's ground ourselves. The sources were clear. There were still major challenges, right? We're not quite there yet.
Definitely not. It's crucial to remember this is still early days.
Yeah.
The biggest hurdle is probably the hardware itself. We're in what they call the NISQ era noisy intermediate scale quantum.
Noisy?
Yeah. The qubits we have are prone to errors. They lose their quantum state, their superposition and entanglement really quickly. That's decoherence. So you can only run relatively short, simple quantum algorithms before the noise takes over.
So the current quantum computers are a bit delicate, finicky.
That's a good way to put it. Plus, as we mentioned, getting classical data loaded efficiently is tricky. And that Barren Plateau issue in training QNNs is a real research problem. And even just getting reliable answers from a probabilistic quantum computation takes effort.
Sounds like some fundamental engineering and maybe even theoretical roadblocks still exist.
They do. But, the progress is incredibly fast. People are working hard on building fault-tolerant quantum computers that can correct errors. And these hybrid algorithms using classical and quantum together are already showing promise for the NISQ era.
And the software is getting better, too. making it easier to actually program these things.
Exactly. Toolkits and platforms are making it more accessible, which is really important for bringing more researchers into the field.
Something else interesting our sources pointed out is not just quantum helping ML, but ML is also helping quantum computing develop. A two-way street.
Yeah, that's a really critical synergy. Classical machine learning is actually being used right now to help physicists control the quantum hardware better, to tune the qubits more precisely.
Okay.
And ML is helping develop better quantum error correction codes, which are essential for fault tolerance. Some researchers are even using ML to help discover new quantum algorithms.
So AI is helping build better quantum computers, which will then run better AI. It's like a feedback loop.
It really is a virtuous cycle. Progress in one area directly helps the other, which could speed everything up.
Okay, so wrapping this up, our deep dive into quantum machine learning, looking at your sources, paints this picture of a field that's, well, just packed with potential, right?
Absolutely. Transformative potential, really.
But with some serious hurdles still to clear, particularly on the hardware side and with some of the algorithms themselves.
True. The challenges are significant, no doubt about it. But the pace of research, the innovation, it's genuinely exciting. The drive comes from the possibility of tackling these currently impossible problems across so many fields.
And as the hardware matures, gets more stable, more powerful, we can probably expect QML to become a much bigger piece of the AI and computation puzzle.
I think that's very likely. This convergence, it really does offer a glimpse into a future where our computational power takes a quantum leap, unlocking doors we don't even know exist yet.
So that brings us to the end of this deep dive into the really fascinating world of quantum machine learning. We've tried to unpack the core ideas, touch on some key algorithms, and look at where it might all lead.
Hopefully it's given you a clearer picture, a feel for why there's so much buzz around this field, even with the challenges.
The journey's definitely just starting, and it feels like there are going to be many more twists and turns. It's certainly a space worth watching if you're interested in where computation and AI are headed next.
Absolutely. Well, thank you for joining us on this exploration today. We really hope it sparked some interest, and we encourage you to keep digging into the areas you found most compelling.